Boost regulator. In a boost regulator, the output voltage is greater than the input voltage, hence the name boost. A boost regulator using a power MOSFET is shown in the circuit diagram. A boost regulator can step up the output voltage without a transformer. Due to a single transistor, it has the high efficiency and the current input is continuous. The circuit operation can be divided into two modes. So mode 1 begins when the transistor M1 is switched on at t equals to 0. The input current which rises flows through the inductor L and the transistor M. This is the equivalent circuit for mode 1 where the current input is flowing through the transistor M back to the source and the output voltage equals to the voltage of the capacitor. So here IC equals to minus IA. Mode 2 begins when transistor M is switched off at t equals to T1 for a period of T2. The current which flowing through the transistor would now flow through the L, DM, C and the load. The inductor current falls until it is transferred to the load. This is the equivalent circuit for mode 2 operation. In this, IC plus I0 equals to I1, I1 equals to IL equals to IS. Here, IC equals to minus IA. Now, the waveforms. When transistor is on, the voltage across the transistor is 0. When transistor is off, the voltage across the transistor is going to present. When the transistor is on, the current flowing through the DM will be 0. This is I1 is the current flowing through DM. During the transistor turn-off period, the current will be maximum at t equals to kT and reduces to 0 at t equals to capital T. Now, in turn-on time, the current across the inductor is going to build from the minimum value to the maximum value. When the transistor is off, the current is going to discharge from the inductor to a minimum value. And this is peak-to-peak ripple between Imax and Iminimum. In some of the textbooks, it is referred as I2 and this is I1. Now, during the turn-on period, IC equals to minus IA, IC equals to IL minus I0. And this value is IC equals to IL minus IA, where IA value is this and IL value is I max here and I minimum here. So it's going to reduce. Now VC. The voltage across the capacitor during the turn-on time will be gradually decreasing to a minimum value. During turn-off time, the voltage across the capacitor is going to build since the current is going to flow through the capacitor. And this difference will give us the peak-to-peak ripple voltage of the capacitor. The output current I0 will be constant throughout. Here the current is supplied by the capacitor and here the current is supplied by the source and this will be IA. Now assuming the inductor current IL is going to rise from I1 to I2, that is I minimum to I max in time T1, then Vs equals to L I2 minus I1 divided by time T1, from which T1 equals to L I2 minus I1 is change in the current peak to peak, so I divided by Vs. That is equation number 1 and this 2. During the turn-off time, inductor current falls linearly from I2 to I1 during T2. During T2, Vs minus this value is Vc. Vc is nothing but V0 and V0 is again nothing but the average output voltage VA. Vs minus VA equals to L, the change in the current, delta I divided by T2. That is equation number 3, from which T2 equals to L delta I divided by Vs minus VA. That is equation number 4. From 1 and 3, equating the delta I value, since the delta I value in both the cases turn on time and turn off period is same, since the peak to peak is same. So equating this delta I values, Vs T1 divided by L equals to Vs minus Va divided by L into T2, from which Va equals to Vs capital T by T2, which is nothing but Vs by 1 minus K. That is equation number 5. Now assuming the lossless system, Vs Is equals to input power equals to output power, so Va Ia, substitute of Va Vs from this, Is equals to Ia by 1 minus K. Equation number 6. Now, a high peak current has to flow through the power transistor since the Is is going to depend upon the duty cycle K, and the output voltage is very sensitive from the equation number 5 to the changes in the duty cycle K, and might be difficult to stabilize the regulator. The average output current is less than the average inductor current by a factor 1 minus K, and much higher RMS current would flow through the filter capacitor, resulting in the use of large filter capacitor and a large inductor than those of the buck regulators. Now, the switching period T equals to 1 by the switching frequency, that equals to T1 plus T2. From equation number 2 and 4, L delta I divided by Vs plus L delta I divided by Vs minus Va. Now, by solving this, you are going to get T equals to 1 by F equals to delta I L Va divided by Vs of Va minus Vs. Sorry, here we got this as Va minus Vs. Let this be equation number 7. Now, the peak-to-peak ripple current delta I from this is given by Vs of Va minus Vs divided by FL Va. Let this be equation number 8. Substituting the value of Vn from the equation number 5, delta I equals to Vs K divided by FL. This is number 9. Now, when the transistor is on, the capacitor supplies the load current for T equals to T1 that we know. Then the average capacitor current during the time T1 is Ic equals to Ia. And the peak-to-peak ripple voltage of the capacitor is delta Vc equals to Vc minus Vc at T equals to 0 equals to 1 by C integral of from 0 to T1 Ic dt equals to 1 by C integral 0 to T1 Ia. That equals to Ia T1 by C is delta Vc. Let this be equation number 10. Let this be equation A. From this equation, we get T1 equals to Va minus Vs by Vaf. Substituting this in the equation number 10, then you'll be getting delta Vc equals to Ia Va minus Vs divided by Vafc, or delta Vc equals to Ia K by Fc. Let this be equation number 11 and 12. This is regarding the boost regulator, operation, waveforms, and the derivations. If this video useful, please like, share, subscribe, and comment.